Hello, chemistry class. This is Mr. Jeans, and today I'm going to talk to you about measurements in chemistry. Now, this is video podcast 1.2, and so what you want to make sure that you do is get out your composition notebook and go ahead and turn over to page 7 and 8. Some of this you should already have from your notebook outline. So we're looking at qualitative and quantitative. Just real quickly, there should be a review for you. Of course, qualitative means it's a description that uses your senses. When you're doing an experiment, these types of observations are very important. You need to tell me what you see, what you hear, if you smell anything. I might tell you in an experiment to test the test tube and feel if it or determine whether it feels hot or it feels cold. All those things are important. And sometimes these are overlooked and they're not recorded in a lab report or in questions, but these things are really important as well. Then we have quantitative. Now, most students remember this because it has the N in it. So N stands for numbers. So quantitative are measurements that have the number, and of course, they have to have a unit as well. So like the time for something to happen, temperatures, how much something weighs, or mass, length. So maybe the solution rose by 45 degrees Celsius, or the length of the magnesium ribbon was 2.5 centimeters or something like that. It has a number and it has a unit as well. So quantitative measurements. All right, now we're going to take a look at scientific notation. And again, this should be a review. Scientific notation is very convenient for us because it's a convenient way of expressing numbers that are either really, really large or really, really small. So the standard format is this: m times 10 to the nth. Well, m is a number that has to be greater than 1 but less than 10. So it's like 1.25 times 10 to some power. Or it might be 5.68 times 10 to some power. Or 9.99. It just can't be 10 and it can't be less than 1. If it is, it's not standard scientific notation. Now, the power of 10, n in this case, is either going to be a positive or negative number. So it'll be a whole number. And if it's a positive number, that simply means that the number is greater than 1. But usually it's because it's a large number. And so that means we use a positive power of 10. If the power of 10 is negative, that means that it's less than 1. So these are generally considered small numbers. All right, so you need to pause the video at this time right here and try these problems out for yourself. Okay, so let's take a look at these problems right quick, and we'll take a look and see how you did on these. Hopefully that you're getting these pretty good. And so I've given you a couple examples there, and if we have 1, 5, 0, 0, 0, 0, 0. Let's see how many zeros I got. 1, 2, 3, 4, 5, 6 zeros. So add one more there. And I've shown you that you have 1.5 times 10 to the 7th power. And then if you have a really small decimal number like this one right here, okay, then the number would be 2.5 times 10 to the negative 5. All right, so the problem that you had to do, that I wanted you to try, was 35,400. All right, so we want the decimal place to be between the 3 and the 5. So we want it to be right there. So that means we're going to need to move the decimal over 1, 2, 3, 4 places. So we write 3.54 times 10 to the what? 4, okay? So that would be the correct scientific notation. All right, if we have 0.0000, 579. Okay, on this one right here, we are going to move the decimal place so that it's between the 5 and the 7. Okay, 5 and the 7. And so we're going to have to move it over 1, 2, 3, 4, 5 places. So that's times 10 to the negative 5 would be your answer there. All right, then the other ones you're supposed to convert it over. So it's 2.47 times 10 to the negative 7th. And so on this one right here, you're going to go the other way. So is this going to be a small number or large number? That's right, it's going to be a small number. So I'm going to write 247. And now I'm going to move the decimal place from here to the left 7 times. So that means I'm going to need 6 zeros. And put my decimal place right there. And so I moved it over 1, 2, 3, 4, 5, 6, 7 to make it into standard notation. Then we have 5.82 times 10 to the 5th power. And so this time, what is this going to be, a small number or a large number? That's right, it's going to be a large number because the power of 10 is positive. So we're going to have 582, and then we need to move the decimal place over 5 places. So that means I need to add 3 zeros. And so that's pretty much it there. Hopefully that is just a review for you, okay? Now let's go back to our slides and take a look here. All right, so accuracy and precision. It's important for us to know the difference between these two, and it's important to know how good the data are. That is the correct grammar because data is, in this sentence, plural. So if you substitute the word measurements in there, you'll see that that would be correct. Now, accuracy is how close a measured value is to the true accepted value. So, for example, if we did a lab and we're figuring out the density of carbon dioxide gas, well, you would find your mass of your carbon dioxide gas in your chemical reaction. Then you would find the volume of your carbon dioxide gas calculated. You would take your mass divided by your volume and get a density. Then you'd want to compare that to the known accepted value for the density of carbon dioxide. Now, where are you going to get that accepted value? Well, what you're going to do is you're going to look it up. Maybe you just go to the internet, you Google it. Maybe you go to a chemistry handbook and you look it up, or a textbook, or maybe I give it to you. And how close you are to that value would determine how accurate you are. Now, precision deals with how close a series of measurements are to each other. And so if numbers are really, really close to each other, for example, if you did the density and you repeated that 3 times like we do in the carbon dioxide lab, and you compared your 3 densities, if they were really close to each other, you would say that your measurements are very precise. Now, I like to use this little illustration. Okay, sometimes you can use targets or something like that. But let's suppose that you have a knife thrower. A knife thrower always has an assistant, right? So there's the assistant, and he stands up against a wall or something like that, or she, and then the knife thrower makes the throws. And in this case, they hit where the X is. So this knife thrower is very good. All right, this knife thrower is able to hit the target that they're looking at. They don't want to hit their assistant because that would be very painful and injuries and possible death. So they hit on the side, very close to the assistant, and all 3 of their hits are very close together. So this knife thrower is very accurate and precise. Now this knife thrower is not so accurate, not so precise. All right, the first throw hits him in the foot. The next throw hits him in the leg. And then the third throw, poor guy, hits him right directly in the chest. So not a good day if you're the assistant. So this person who's throwing this knife, he or she is not very accurate because obviously not trying to hit the person, but they did 3 times. Not very precise because their throws are just all over the place. Now this one is precise, but not very accurate. Okay, not a good day for sure for the assistant. The knife thrower, very close. All the throws are really close to each other, but a little bit off the mark. Don't want to hit your assistant with 3 knife throws. So that's precise but not accurate, okay? All right, so how can you tell if data are accurate? Well, the accuracy of a measure is expressed by what we call percent error. And so what you want to do is use this little formula. So copy these steps down. First thing you want to do in finding your percent error is calculate the error. Now the error, you take your experimental value, that value that you find in the lab, and you subtract out your accepted value. All right, again, the accepted value would be what you would look up. And you find the difference between those two. Now notice the lines. What do those mean? Absolute value. So in absolute value, do we have negatives? No. So if you get a negative in your calculator, you just drop the negative and you always use positives. And then you just calculate the percent error. You take the answer from number 2 and you divide it again by the accepted value. So it's the error, okay? And then you divide it by the accepted value, and then you multiply by 100. Now you want your percent error to become very low. The lower the percent error, the more accurate your measurements are. The higher the percent error, the less accurate your measurements are. And so you want a percent error in a lab of less than 10%. Those are great labs. All right. If you have higher than 10%, it might not be your fault. It could be just the lab itself that produced that good of results, but it could be that you messed up somewhere in your procedures, or you measured something wrong, or you got some sort of a contaminants or something like that. So the lower the percent error, the better off you are. Okay, so two ways we can tell if data are precise. All right, we measure precision based upon the number of decimal places that are shown in the value, okay, in the measurement. So 18.0 grams versus 18 grams. Now, value of 18 and 18.0 are the same. So we treat them the same way when we calculate, but 18.0 has three significant figures in it, where 18 only has two significant figures. And so 18.0 gives us more information. It's all the way down to a tenth of a gram, where 18 is just one up to the nearest ones place, okay? Second of all, we see how close a set of measurements are to each other. So if all your measurements like this one, 10.32 grams, 10.33 grams, and 10.31 grams, if they're all real close like these are, you can say that your measurements are precise. So those are the two ways you can tell. All right, now let's talk about significant figures. I mentioned that a moment ago. Significant figures are important in science, especially for chemists and especially for physicists. Now, you don't usually talk a lot about them in biology class or anatomy class. You almost never talk about them in math class. But these are important things to really look at, because we're dealing with real data, and chemistry is a quantitative science. That means we measure stuff and we get data, and then we need to analyze that data, do calculations. So significant digits are digits that come directly from the measurements. All right. Now, don't get confused. If I say something is not a significant digit, I am not saying that it is unimportant. Zeros are still important, even if they're considered not significant, okay? So the terms that we're using here, you got to be very specific. This is in the terms of measurement. Significant and not significant do not mean important and not important, okay? All digits in a measurement are important, whether we consider them significant figures or not significant figures. Okay, so here are your rules for significant figures. So you'll want to pause the video and jot this down. You should have also got these from the textbook. Okay, so number one says that non-zero numbers in measurements are always significant. So anything other than a zero is always significant. Doesn't matter what. So what does always mean? It means always. It means all the time. So 35 grams would have two significant figures. 256 milliliters, three significant figures. All right, rule number two, jot this one down. All right, zeros between non-zero numbers are always significant. I call this the sandwich rule. So if zeros are between non-significant figures, they are significant. So 202 is three significant figures. 2002 are four significant figures because the zeros are sandwiched in between the twos. All right, number three, jot this one down. Zeros to the left of all non-zero digits are never significant. I call these leading zeros. Zeros that are to the left of non-zero digits, never, ever significant, okay? Never means what? It means never, okay? It means never, ever. So 0.02 grams has only one significant figure. The zeros at the beginning are not significant. Then 0.000034 has two significant figures. Now, are those zeros important? Yes. 0.00034 is not equal to 0.34. So those zeros are significant. However, the zeros are placeholders. So we call them non-significant figures. They're important, but non-significant. And then number four, got this rule down. Zeros to the right of all non-zero digits are only significant if there's a decimal explicitly shown. So in these examples, 2.00 grams, those zeros are to the right and there's a decimal, so those three significant figures. However, if you look at 200 grams, those zeros are to the right, but you don't see a decimal. So it's only one significant figure. Now, in this third case, 10 decimal, notice there's not a zero after it, and it should be a little g there. That number would be two significant figures. That's shown because maybe you did a calculation, you came up with the number 10, but you should only have two significant figures. So you put the decimal place there, indicating that that zero is significant. And again, if you put 10.0, then you would have three significant figures. So that's just a case there. All right, and then finally, if you have scientific notation, it's real easy. Everything in front of the times 10 symbol is significant. So 2.0 times 10 to the second grams is two significant figures. Now, really, this comes important when we do calculations. Okay, so pause the video here for a few moments, and you'll want to do these examples right quick. All right, so I'm going to pause my video as well. Okay, so take a look at these examples for just a few moments here, and these are the ones that I told you to write down. So when you look at this first one right here, the leading zeros are to the left of all non-zero digits, so they do not count. This 2 would count, this 1 would count. This 0 is sandwiched, so it would count. These zeros are to the right of all non-zero digits, and there's the decimal, so they would count as well. So how many do we have? 1, 2, 3, 4, 5, 6, right? We count again. Yep, 1, 2, 3, 4, 5, 6. All right. Now take a look at this one. This 3 obviously counts. These zeros are leading zeros. They don't count. These are after the non-zero digit, and there's a decimal, so we would have 3 significant figures in letter C. Okay? All right, this one, the 2, the 4, and the 1 would count. These zeros are sandwiched, so they count. These zeros are after the 1, and there's a decimal, so they count. So how many do we have? 1, 2, 3, 4, 5, 6, 7 significant figures for that one. I hope you got that one. All right, this next one, the 2, the 3, and the 1 count. These zeros are sandwiched, so they count. Now, these zeros are to the right, but is there a decimal in that number? No, there's not. So they are not significant. They are just placeholders. So you have 1, 2, 3, 4, 5 significant figures. Are those zeros important? Yes, they have to be in the number for the number to be accurate, but they're just placeholders, so we call them non-significant. Okay, for D, you have the 2 and the 4 and the 1. These zeros are sandwiched, so they count, but this 0 on the end would not count because there's no decimal. So you have 1, 2, 3, 4, 5, 6, 7 significant figures in that number as well. Now in this one, letter F, all these zeros are leading zeros, so only the 2 and the 1 count. So that is 2 significant figures. All right. So hopefully you've got that. Sometimes that confuses some students, but hopefully you're on track with significant figures here. All right. Next slide. All right. When this really comes into play is when you do calculations. Calculations must reflect the values of the data used in the calculation. We can't have infinitely significant answers. All right, so when you multiply and divide, there's a rule, and when you add and subtract, there's a rule. So pause the video here, jot down this rule. Okay, we're back. So when you're multiplying and dividing, the answer should have the same number of significant figures as the value with the least number of significant figures. All right, so if you've got a calculator, do this problem. If you don't, pause the video, grab a calculator. Okay, you're back. Now take in your calculator, take 34.0. You don't really have to do the 0.0 in the calculator, but it's a significant figure. 34.0 divided by 10.33. And what do you get? Well, you should get something like this in your calculator, okay? 3.29138. So in the past, maybe a teacher said, well, just round it to 2 decimal places or round it to 3 decimal places or something like that. Not anymore. In chemistry, we go by significant figures. So you have to look at your problem. 34.0, how many significant figures is that? Well, that's 3 significant figures. 10.33, that's 4 significant figures. So you've got to go by the least number of significant figures, which is what? It's 3. 34.0 only has 3. So we're going to round this off to 3 significant figures. So we're going to look at 3.29, and we're going to look at the digit just past it, the 4th digit, and it's a 1. So if it's below 5, what do? We keep the number the same. If it's above 5, we're going to go ahead and round up. So this number should be rounded to 3.29. That gives you 3 significant figures, which matches what is in your answer. Okay? Now, here's some problems for you to solve. Pause the video right here and jot these problems down and give them a try. Okay? All right, so I'm going to go on and talk about addition and subtraction, and then we'll come back to these problems and see how you're doing. All right, here's the rule for addition and subtraction. It's a little different. The answer should be rounded to the last significant figure of the least precise value. So in this case, we look at our numbers and we say, which one's rounded to the least precise place value? Now, if it's decimal numbers, it's real easy, but if it doesn't have decimal numbers, we got to be careful. So let's do this problem, 220 plus 14.5. Well, that's pretty easy, 234.5. However, when you look at this, the 220 is rounded off to the tens place. The 14.5 is given to us in the tenths place. So which one is least precise? Tens place or tenths place? Well, it's the tens place. So we need to round this number off to the tens place. So we have 234.5. So the tens place is the 3. So we look at the 4. Now we don't carry all the way out. We ignore the 0.5. That gets forgot about. It doesn't make the 4 or 5. So we just look at the 4. The 4 is going to keep the 3 the same. So how do we round this? 230. We don't round it to 23 because that would lose the value. We put a 0 in there, so we're saying that it's to the 230 grams because 234.5 is not going to round to 23. It's going to round to 230. Okay, here are a few examples for you to solve on your own there, and we'll see how you do. Okay.